Hello, everyone, and welcome to Chromatography Fundamentals. So this is the theoretical foundation for everything that follows in this series. HPLC, GC, and all the specialized chromatographic techniques are specific applications of the ideas we will develop here. I recommend watching this with a calculator nearby because there are 5 worked examples. Feel free to pause at each one and try the calculation yourself before I walk through the solution. Let's start. So here are the 7 learning objectives for this lecture. Notice that there's a logical progression to them. We start with a single analyte and ask how it behaves in a column, and this is the partition coefficient. Then we compare 2 analytes, that gives us selectivity. Then we ask how good is the column, that is plate theory. Then we ask how do we make it better, that is the Van Demeter equation and optimization. Each concept builds directly on the previous one. By the end of the recording, you should be comfortable with all 7 of these objectives and ready to apply them to real chromatographic data. So in today's lecture, here's the roadmap. We'll cover 6 sections. They can be seen here. I suggest watching straight through the first time for the big picture and then revisiting specific sections as needed. Okay. So let us start with the most fundamental idea in all of chromatography. Look at the diagram on the right. The bottom region represents the stationary phase. I've drawn it with spherical particles, which is what you would see in an HPLC column. The little lines on each particle represent the bonded phase, the chemical coating that interacts with anions. Top region is the mobile phase, flowing from left to right. Now look at the 2 compounds. Compound A in red has a large partition coefficient, K. Count the red dots. 5 are in the stationary phase and only 1 is in the mobile phase. Compound A strongly prefers the stationary phase, so it moves slowly. Compound B in green is the opposite. 5 dots in the mobile phase and only 1 in the stationary phase. It has a small k and moves quickly. The double arrows at the interface represent the dynamic equilibrium. Molecules are constantly transferring between the 2 phases, but the average distribution is determined by k. The difference in K values is the entire basis of chromatographic separation. If you understand this single diagram, you understand the core principle of every chromatographic technique. Okay, so from K to the chromatogram. Now we connect the thermodynamic partition coefficient K to what we actually measure in the chromatogram. Look at the chromatogram on the right. The first tiny spike at time 0 is the injection. The peak labeled void at Tm of 1.2 minutes is the unretained marker, a compound that does not interact with the stationary phase at all and simply passes straight through. Then our 2 analytes appear, A at 5.4 minutes and B at 6.1 minutes. The retention factor K is the experimentally accessible version of capital K. It equals the adjusted retention time, that is TR minus TM, shown by the bracket divided by TM. Think of K, small k, that is, as answering this question. For every minute this compound spends moving with the mobile phase, how many minutes does it spend sitting in the stationary phase? A K of 3.5 means the compound spends 3.5 times longer in the stationary phase than in the mobile phase. The ideal K range is somewhere between 2 and 10. Below 2, compounds elude too close to the void and separation is poor. Above 10 or 20, and you're waiting unnecessarily long. You'll notice that I have marked the base widths WA and WB with gold brackets. We will need those shortly for resolution and plate count calculations. Now we move on to selectivity. Can we tell 2 peaks apart? Selectivity alpha answers the question, does the column chemistry actually differentiate between 2 analytes? It is the ratio of their retention factors, always defined so that alpha is greater than or equal to 1. Look at the 2 diagrams on the lower right. When alpha equals exactly 1, the 2 compounds produce perfectly overlapping peaks. They co-elute. No amount of column length, no change in flow rate, no increase in plate count will separate them. The only way to fix this is to change the chemistry. A different column, a different mobile phase, a different pH, a different temperature. When alpha is greater than 1, as it is in the lower diagram, at alpha equals 1.17, the peaks have different retention times. There is a thermodynamic basis for separation. This is the critical concept to internalize. Alpha is a thermodynamic property that depends only on the chemistry. It does not depend on the flow rate, column length, or injection volume. Those are kinetic or instrumental parameters. The list on the right shows the practical levers for changing alpha. Different stationary phase, different organic modifier, pH adjustment, ion pair reagents, or temperature changes. Each of these alters the equilibrium position of one or both analytes. So let's look at the resolution. Resolution, RS, is the single most important number in chromatography. It tells you how well two peaks are actually separated on the chromatograph. The formula is straightforward. Twice the distance between peak maxima divided by the sum of their base widths. Study the four visual examples on the right carefully. At RS of 0.6, the peaks overlap heavily. I have shaded the overlap region to emphasize this. You cannot accurately quantify either analyte. At RS of 1.0, you can see two distinct maxima, but there's still about 6% overlap between the peaks. At RS of 1.5, there's now a clear baseline between the peaks. This is the regulatory standard from USV chapter 621. At RS of 2.0, there's a generous empty baseline, but you've spent extra analysis time to achieve it and is unnecessary. The key insight is that RS captures both thermodynamics and kinetics. The numerator, the peak spacing, depends on selectivity. That is thermodynamics. The denominator, the peak widths, depends on column efficiency. That is kinetics. This is why resolution is the bottom line metric. It integrates everything about your separation into a single number. Okay, so now we're going to go into our worked example number 1. And I'll encourage you to pause the video here and try this calculation yourself before we walk through it, okay? So here you have a void time of 1.2 minutes. Analyte A at 5.4 minutes with base width 0.35, and analyte B at 6.1 minutes with base width 0.40. We're asked to calculate Ka, Kb, alpha, and Rs. Okay, let's go through it. So for Ka, 5.40 minus 1.20 gives 4.20, which divided by 1.20 equals 3.50. For Kb, we have 6.10 minus 1.20, which gives 4.90, then divided by 1.20 equals 4.08. Both values fall in the 2 to 10 sweet spot, so we're good. For selectivity, alpha equals Kb over Ka, so 4.08 divided by 3.50, which equals 1.17. So this is moderate selectivity. The column does differentiate the two compounds, but they're not dramatically different. For resolution, 2 times 6.10 minus 5.40 divided by 0.35 plus 0.40, that is 2 times 0.7 divided by 0.75, which equals 1.87. Since this exceeds 1.5, these peaks are baseline resolved, and this method would pass system suitability. These numbers will reappear in later worked examples, so please try to remember them. Right, so moving on then. Now we're going to shift our focus, and we're going to be asking, where does each peak appear? From where does each peak appear to asking how sharp are the peaks? And this is the domain of plate theory. Now have a look at the diagram on the right. It shows both methods for measuring peak width on the same Gaussian peak. The red dashed lines are tangent lines drawn at the inflection points of the peak, where they intersect the baseline, defines the base width W, which spans approximately 4 sigma. The green bracket shows the width at half height, W1 half, which spans approximately 2.355 sigma. The base width plate count uses the formula N equals 16 times TR over W quantity squared. The half weight formula uses N equals 5.54 times TR over W half quantity squared. For a perfectly Gaussian peak, both methods give the same N. In practice, the half-height method is preferred because it is less affected by peak tailing. When peaks tail, the tangent method overestimates the base width because the tangent lines follow the slow decay on the backside of the peak. The half-height method only looks at the upper 50% of the peak, where the Gaussian shape is better preserved. I always recommend calculating n both ways and comparing. If they disagree significantly, you have a peak shape problem, which is typically tealing. Let's have a look at worked example number 2. So again, as usual, take a chance to pause and go through it yourself before we have a go ourselves. So this example illustrates a crucial practical point. Calculate n by both methods for a peak at 12.45 minutes with base width 0.72 and half height width 0.18 minutes. Using the base width method, n equals 16 times 12.45 over 0.72 squared, giving about 4,800. Using the half height method, n equals 5.54 times 12.45 over 0.18 squared, giving about 26,500. That is a factor of 5.5 difference, but what does this actually mean? For a perfectly Gaussian peak, the base width should be about 1.70 times the half height width. Here, 0.72 divided by 0.18 is 4.0, which is much larger than 1.70, and this tells us the peak is significantly tailing, i.e. the front half is sharp, there's a long, slow tail on the back. The tangent method captures that tail and inflates the base width. The half-height method is relatively robust to this. In a real lab report, you must report both findings. If they disagree, calculate and report the tailing factor as well, and investigate the cause. It might be secondary silanol interactions, column degradation, or a mobile phase pH issue. So what causes band broadening? Plate theory tells us how many plates we have, but not why plates broaden and why peaks broaden. Rate theory, developed by Van Demeter and co-workers in 1956, identifies 3 independent mechanisms. Look at the 3 diagrams. The A term, eddy diffusion, is shown on the left. In a packed column, molecules take different paths through the particle bed. I have drawn 2 paths in red and green. They have different lengths, so molecules arrive at the detector at different times. This creates broadening that is independent of flow rate. Importantly, the A term is 0 in open tubular capillary columns because there is only one flow path. The B term, longitudinal diffusion, is shown in the center. Even if flow stops, molecules diffuse along the column axis from regions of high concentration to low concentration. The top shows a narrow band at time 0. The bottom shows how it spreads over time. This effect is inversely proportional to flow rate. At slow flows, molecules have more time to diffuse. The B term is especially important in GC because gas phase diffusion is about 10,000 times faster than liquid phase diffusion. The C term, mass transfer resistance, is shown on the right. I've drawn a cross-section of a porous particle. A molecule at the outer surface equilibrates quickly. but a molecule deep inside the pore takes time to diffuse in and out. At high flow rates, the mobile phase sweeps past before equilibrium is reached, causing browning. Smaller particles reduce the C term because the diffusion paths are short. The Van Deemter equation. The Van Deemter equation is, and shown here at the top in the box, H equals A plus B over U plus C times U. It is one of the most important equations in chromatography, and you can study the plot on the left carefully. The red dashed line is the A term, constant and independent of flow. The green dashed curve is B over U. It falls steeply as flow increases because faster flow gives less time for diffusion. The blue dashed line is C times U, which increases linearly with flow because faster flow means less time for equilibration. The solid blue curve is the sum of all three. There's a clear minimum at U opt, marked with a gold dot. I have shaded the practical operating range in light blue. Notice how the curve is quite flat between about 7 and 18 centimeters per second in this example. This flatness near the minimum is extremely important practically. It means you can operate well above U opt with only a modest loss in efficiency. Chromatographers exploit this routinely. They sacrifice 5 to 15% of plate count to save 30 to 50% of runtime. The formulas on the right give the optimal velocity as the square root of B over C, and the minimum plate height as A plus 2 times the square root of B times C. Let's have a look at our third worked example, the Van Deemter optimization. Again, pause and have a chance to go through it yourself before we go through it together. So we want to calculate U opt and H min for A equals 0.05, B equals 0.50, and C equals 0.005. The optimal velocity is the square root of 0.50 divided by 0.005, which is the square root of 100, equal to 10 centimeters per second. H min is 0.05 plus 2 times the square root of 0.5 times 0.005, which is 0.05 plus 0.10, which equals 0.15 centimeters. Now look at the table on the right. This is the practical payoff. At 15 centimeters per second, 50% above optimal, H only increases 5.6%, barely noticeable on the chromatogram, but your runtime decreases by a third. At 20 centimeters per second, double the optimal, H increases by 17%, but now analysis time is halved. In a high throughput QC lab, running hundreds of samples per day, saving 5 minutes per run is absolutely worth a small loss in plate count. This table is the kind of analysis you should do for your own methods. So let's have a look at the Van Deemter equation in different techniques. This four-curve comparison is essential for understanding why different techniques behave so differently. Start with conventional HPLC at the top in blue, significant A term from the packing, moderate B term, substantial C term, the minimum low velocity, and the curve rises steeply on the right. Now look at UHPLC in red, with 1.7 micrometer particles, both A and C are dramatically reduced because smaller particles mean shorter diffusion paths and more uniform packing. The curve is lower and flatter, meaning you can push the flow much harder without losing efficiency. The gold curve shows core shell particles at 2.7 micrometers. These nearly match UHPLC performance, but at conventional HPLC pressures. The solid core eliminates the long diffusion paths inside the particle. This has been one of the most important practical advances in the last 2 decades. Finally, the green curve is capillary GC. No A term because there are no packing particles, a very large B term because gas phase diffusion is fast, which is why the curve rises steeply at low velocities. But the C term is tiny, so the curve stays very flat on the right side. Capillary GC achieves the lowest absolute plate heights of any technique. The Purnell or fundamental resolution equation, also called the fundamental resolution equation, is the master equation of chromatography. It decomposes resolution into 3 independently controllable factors. The efficiency factor, the square root of n over 4, has a square root dependence. This means doubling N only improves resolution by a factor of 1.4. To double resolution by efficiency alone, you need 4 times the plates. Very expensive in terms of time and pressure. The selectivity factor is the most powerful lever. Look at the numbers. Increasing alpha from 1.05 to 1.1 nearly doubles this term. Small changes in chemistry produce large changes in resolution. The retention factor term is shown in the plot at the bottom. It increases steeply at low K values, going from K equals 0.5 to K equals 2, doubles the term. But above K equals 10, shown by the dashed line, the curve flattens out. Further increases in K give negligible improvement. This is why we define the optimal K range as 2 to 10. Below 10 or below 2, you're leaving resolution on the table. Above 10, you're wasting time for marginal benefit. The shaded green region marks this sweet spot. The practical lesson is pretty clear. If your resolution is poor, change the selectivity first. Only as a last resort should you try to brute force it with more plates. Let's try our fourth worked example, and as always, pause and check it before moving on. So this example quantifies exactly how expensive it is to rely on efficiency alone. With an alpha of only 1.05, the selectivity term is very small at 0.0476. With K2 of 5.0, the retention term is 0.8333. Multiplying these gives 0.0397. Now, for RS of 1.0, you need about 10,000 plates. For RS of 1.5, you need about 23,000. For RS of 2.0 over 40,000, going from RS of 1.0 to 1.5 reduces 2.25 times more plates, or requires 2.25 times more plates. Going from 1.5 to 2.0 requires another 1.78 times. But here's the key insight. Stated in the blue box at the bottom, if you could improve alpha from 1.0 to 1.10, the selectivity term doubles. That means the required plate count drops by a factor of about 4. Instead of 23,000 plates for RS of 1.5, you would need only about 5,700. Same column, much shorter, lower pressure, faster analysis. This is why selectivity is the most powerful lever and why you should always be your first optimization tool. The fifth work example is, again, another chance to pause and go through a real-world scenario on your own before we go through it together. So as I said, this is a real-world method development scenario. You have RS of 1.10, which is below the 1.5 target. You have two options. Option A is brute force, increase the column length. Since resolution scales is the square root of length, you need L nu equals 15 times 1.5 over 1.1 quantity squared, which is 15 times 1.86, giving 27.9 centimeters. Round that up to a 30 centimeter. But that nearly doubles your runtime and doubles your back pressure. Option B is smart, change the chemistry. Suppose switching from acetonitrile to methanol changes the alpha from 1.08 to 1.12. The ratio of selectivity terms is 0.1071 divided by 0.0741, which is 1.45. The new resolution is 1.10 times 1.45, which equals 1.59. That passes 1.5 on the same 15 centimeter column, same runtime, same pressure. So option B wins decisive. This example is the single best illustration of the optimization hierarchy. Selectivity first, then retention, then efficiency. In your own work, always exhaust the chemistry options before reaching for a longer column. How do we improve separation? This flowchart summarizes the optimization decision process. Start at the top. Is RS below 1.5? If yes, the first question is always, can I change the selectivity? Try a different column chemistry, a different mobile phase composition, a different pH, or a different temperature. This is the most powerful approach. If you cannot change selectivity, perhaps you're locked into a compendial method, then check whether K is in the 2 to 10 range. If K is too low, reduce the organic fraction to increase retention. If K is too high, increase organic to speed things up. Only as a last resort, at the bottom of the flowchart, should you try to increase plate count by using a longer column. Smaller particles are lower flow. The dashed feedback arrows show that after each change, you re-evaluate. Did RS reach 1.5? If not, continue down the flowchart. Remember, doubling N gives only 1.4 times improvement in RS, while a small change in alpha can double RS. This hierarchy should become second nature. So here are our key equations for your reference. So I recommend taking a screenshot or printing this slide for your own use. These 8 equations form the complete theoretical toolkit for chromatography. The retention factor K describes a single analyte. Selectivity alpha compares 2 analytes. Resolution RS quantifies separation quality. The plate count N and plate height H describe column efficiency, and I have included both the base width and half height formulas since you should routinely calculate both. The Van Deemter equation predicts how efficiency depends on flow rate, and the Purnell equation connects everything together by decomposing resolution into 3 contributing factors. You need to know all 8, understand what each quantity means physically, and be able to apply them. They will appear in assessments and in every subsequent lecture in this series. Okay, here are today's takeaway. So let me recap the 7 key ideas. First, partitioning is the core mechanism. Everything else follows from differential distribution between mobile and secondary phases. Second, K is your primary experimental measure of retention. Aim for 2 to 10. Third, alpha is purely thermodynamic. Only chemical changes affect it, and it is the strongest lever for improving separation. Fourth, RS of 1.5 is the practical target for baseline resolution. Fifth, calculate plate count by both the base width and half height methods. Compare them to diagnose peak shape problems. Sixth, the Van Deemter equation explains the trade-off between diffusion at low flow and mass transfer lag at high flow. Seventh, the optimization hierarchy. Selectivity first, then retention, then efficiency, never the reverse. In the next lecture, we will apply all of this theory to the most important chromatographic technique, high-performance liquid chromatography. I recommend reviewing the equations on the previous slide before watching that lecture. Any questions? Please let me know. Thank you.